All right, so now we're going to talk about the way water moves through the ground. This is a really important part of, probably the most important part of hydrogeology. and uh, in order to understand that, we need to understand a little bit about a couple of different characteristics of the way the water moves through the ground. And so, all right, so water is stored in things called aquifers. An aquifer is a geologic material that can store and transmit usable quantities of water. So it's got to be able to have enough porosity to hold on to store a lot of water. And then those pores have to be capable of allowing the water to flow through. And the ability of material to allow water to flow through is generically referred to as permeability. So if something's permeable, it's like stuff can move through it. If you're playing basketball and you have a permeable defense, right, that means the other team's able to move through and score baskets, score points. So permeable is just how easily stuff, whatever it is, moves through a material. And when we talk specifically about water, which is what we're talking about 99.999% of the time in hydrogeology, we give it a new name, and that's hydraulic conductivity, which is basically the same thing. It's just specific to water. And hydraulic conductivity is abbreviated as a capital K. So hydraulic conductivity is permeability with respect to water. And it's in units of distance over time, usually centimeters per second. All right, or feet per day or whatever. Okay, so when you think about hydraulic conductivity, and we think about the flow of water through aquifers, one thing that we need to realize is that all geologic media are not the same, all aquifers, all rocks and sediments and so forth. So you can imagine some grains of sand that are stacked like this on top of each other. And if you have something that looks like this, then you can imagine that water could move this way just as easily as it moves this way. And that water moving over in here, in this part of the material is going to be able to move just as easily as it can over in here. So it can move in any direction with the same degree of ease, and no matter where you are, it's always moving at has the same properties. And we refer to these as the homogeneity versus heterogeneity, and isotropy versus anisotropy of the aquifer. So homogeneity versus heterogeneity, we can think of, the way I like to explain this is with arrows, right, with vectors. So if you have a line that looks like this, what it's saying is the water is moving left to right, and the length of the arrow is proportional to the hydraulic conductivity. So a pretty long arrow like this would suggest that the water can move left to right pretty easily. It's got a high hydraulic conductivity. A short arrow like this would say that the water has a harder time moving left to right. So that the length of the arrow is proportional to the K, hydraulic conductivity, right? And the direction of the arrow reflects the direction of water movement. Okay. So we can imagine having something that looks like this. I'll draw two arrows here. So what this is supposed to represent is the water moving up and down, north-south versus east-west. And you notice that the length of the arrows are the same. And so that's an example of isotropy, right? So that the water is capable in moving this way and this way in any particular spot. It's able to move right, left, and up and down with the same degree of ease at one particular spot. So that's isotropy. Anisotropy would look maybe something like this. Scoot this up here. So what this is saying is that the water can move north-south a lot easier than it can move east-west, and that's anisotropy. Then we can have heterogeneity and homogeneity. So now instead of looking at it in an individual point, we're going to look at it in two distinct points. So here is one point in the aquifer, and here is another point in the aquifer. And the length of the arrows is the same at two different points. So that's telling us that the aquifer is homogeneous, homogeneity. If we had two different points in the aquifer with very different hydraulic conductivities in the same direction, that would be heterogeneity. And then, of course, you can imagine, get another piece of paper. You can imagine something where you have anisotropic homogeneity, which would be something like this. Two different points have anisotropy, but they have the same degree of anisotropy. Or you could have isotropic heterogeneity, which would be something that looks like this. Two different points have, at any given point, the water can move north, south, and east, west with the same ease, but it's having a much harder time moving at this point than it is at this point. The hydraulic conductivities are bigger. The arrows are longer here. So you can have all sorts of mixing and matching. Now, what kind of geologic materials could produce those kinds of situations? Why would you ever have something like anisotropic homogeneity? Well, a classic example would be, we talked earlier about how sedimentary rocks produce, are deposited in beds. Each one of those things is a bed. And the lines that connect one bed to another, which are, see if you guys remember what those are called. Anybody remember what those are called? Bedding planes in blue here. Those are zones of weakness. Bedding planes. And they're zones of weakness. So water can move a lot easier in this direction along the bedding planes than it can moving north-south or up and down through the rock layers themselves. So that would be an example of anisotropic homogeneity, where no matter where you go, the water is moving with the same ease. Those are supposed to be the same length, and I'm not doing a good job, along the bedding planes, and with the same lesser ease north-south through the rocks themselves, and so forth. So beds, fractures, you imagine that if you had a rock that looked something like this, just like a crystalline igneous rock, something that had cooled, something like a granite, right? Water would have a very hard time moving through that in general, but what if the rock had, through tectonic processes, through the uplift, crushing together of tectonic plates or something, had developed a whole bunch of fractures like this, right? Well, water would have a much easier time moving through the fractures, moving in this direction, than it would moving east-west through this, or in any other direction, if it wasn't moving through the fracture. So that's hydraulic conductivity. One more thing to talk about, I guess, with hydraulic conductivity, and that is the scales here. The hydraulic conductivity can vary by a lot. The hydraulic conductivity of different materials can vary by literally about 1 billion orders of magnitude. So let's give you a list here of some possibilities. We could have a well-sorted gravel. You guys all know what gravel is, pretty big chunks. Well-sorted gravel can have a hydraulic conductivity, say, of 10 to the first centimeters per second. And if you're not used to these exponents, it basically is telling you how many zeros you have there. So 10 to the first would be 10. I'll just write them over here. 10 to the first would be 10. 10 to the 0 would be 1. 10 to the minus 1 would be 0.1. 10 to the minus 2 would be 0.01, and so forth. So a well-sorted gravel could have about as high a hydraulic conductivity as you'll ever see in nature, which is about 10 to the first. I'll give you more specifics on these a little bit later when we start talking about it. But at the low end of the scale, that would be at the high end of the scale, would be something like a densely packed clay or shale. And those can have values of 10 to the minus 10 centimeters per second. So every one of these numbers, every one of these exponents, that's a factor of 10. So this is 10 times, so this is a difference of about 1 billion or 10 billion times. Water will flow through a well-sorted gravel about 1 billion or 10 billion times faster than it would flow through a densely packed clay. And obviously, therefore, hydraulic conductivity plays a really, really important role in determining how fast water can move through the ground.